My name is Paul Edison-Lahm. I'm the Communications Director and past President of the Geological Society of the Oregon Country. And we are the oldest collaboration of amateurs and professional geologists in the Pacific Northwest. We have been stopping the car and pulling over at outcrops for over 86 years and bringing field trips and lectures to the Portland metropolitan region and Portland State University. Someone asked earlier, set up this question. The Oregon Country is a territorial concept that included the states of Oregon, Washington, Idaho, a little bit of Wyoming. It was, I guess if we went back to our pre-1846 boundaries, we could march up to Vancouver and claim British Columbia. But in fact, the reason that the title Oregon Country was chosen by Professor E.T. Hodge at University of Oregon back in 1936 is that it roughly encompasses the watersheds of the Snake and Columbia rivers. In fact, most of us are in the northwest corner of Oregon in the either Willamette Valley or Portland metro area, but especially the Portland Basin. So that's the Portland Basin. It's a roughly rectangular tectonic basin. It's about 20 miles across, about 50 miles long. And the interesting thing about it is, though it has two rivers in the middle of it, it has the Willamette running north into the Columbia, which runs out to the ocean. The rivers did not carve the basin. The basin is a tectonic basin that opened up and I guess essentially captured the rivers. I live down here in Southeast Portland, very near Reed College, where I resettled about 41 years ago. Although before that, I lived in a little town some of you may have heard of in Southern California called Northridge. And my interest in geology was spurred rather abruptly in February 9th, 1971 by the Silmar earthquake.
Yep.
So that is something that we Oregonians and Californians have in common, is we are living on an active plate boundary. We are living on the active edge of the North American continent compared to the passive edge of those folks back on the East Coast. Now, if you were here 200 million years ago, it was just ocean. There was no land here. It was nothing but ichthyosaurs and plesiosaurs and other small dying creatures. So the question for tonight is, where did all this land come from? Where did all this rocks and mountains and dirt and so forth? And I'll try to answer that, giving the geological story, starting kind of in the middle of the story of Earth, with the breakup of Pangaea, the supercontinent that the dinosaurs lived on 280 million years ago, started to split down the middle, and Africa, Europe, Asia went one way, and the Americas went the other way, leaving the Atlantic Ocean in their wake. So for the past something million years, the North American continent has been pushing to the west. What that means for those of us on the West Coast, and those of us especially in the Pacific Northwest, is the phenomena of subduction, which is when the continent encounters the oceanic plate. The oceanic plate, which is heavier and denser and full of water, descends underneath the continent, which is, despite the fact that it has mountains on it, lighter. So that's where all of our story starts, because anything on that oceanic plate, be it sand or rocks or fish or seashells or tin cans or even islands, gets smashed up against the continent. And that's the process of accretion. And in our case, in Washington and Oregon, the particular accreted block that we're concerned with is called Siletzia. And it was a volcanic island about 56 million years ago. Imagine, a sort of arc volcanic like Japan, for example. And it erupted 56 million years ago, but 50 million years ago, you don't have to remember the dates, it was accreted, smashed into the side of the continent. So that's the first answer to our first question, which is, how did the land come from? Where did the land come from? The first land building episode was the accretion of Siletzia. And in fact, it turns out that the entire West Coast is just an accretion of these terrains, Terranes. So all the way down from Mexico, all the way up to Alaska, it's just one terrain wreck after another. And that's how the West Coast, which is geologically young compared to the East Coast and the Appalachians and so on, that's how the West Coast was assembled. What has some new evidence just in the past, well, 2 decades, but still geologically, that's not very long. We've discovered that Siletzia is actually the result of a volcanic hotspot, much like the Hawaiian hotspot. So looking again at the Portland Basin, that little corner of Northwest Oregon, and kind of blowing that up, I'm going to superimpose a geologic map on top of it. And so there you see the dark red is where Siletzia outcrops, and the lighter, the pink, is where it is presumed to have been smashed up and accreted to the continent. So zooming in a little bit here to the Portland Basin, we see that the entire bedrock is that Siletzia basalt or Waverly basalt. So here it is outcropping. This is at the Waverly basalt, about 3 miles from my home, on one of the field trips that we do with, it's a bike tour. And you can see it's this very old crumbly basalt. It's about 56 million years old. It's spent a lot of time in the water. And so one of the things that happens when that occurs is that the water percolates through the basalt, it picks up any silica, and it redeposits them in these nice little zeolites inside of the vugs, the heulandite. And I mean, you folks probably know your zeolites better than I am. Some of them are quite pretty. This one is, sort of the way it looks, but it's very crumbly basalt. You can start to take it apart, and a lot of it will just fall apart in your hands. The plate is coming in at an angle, and what this does to Oregon and Washington is it kind of torques them. I don't think that's the right geological term, but it twists the entire state. And the smaller arrows that you're seeing there in the diagram are the velocity vectors of GPS units that are placed around the 2 states. Oh, my earphone fell out. And what it shows, and this is picked up in the paleomagnetism of the basalt too. What it shows is that for the past millions of years, there's been this rotation, this breaknecking rotation of 1 degree every million years. And so the entire state of Oregon and Washington are undergoing this clockwise rotation. The local effect of that is to create these pull-apart basins, or rhombochasms, where you have the sort of strike-slip faults that are in parallel, and then you have a piece that's dropping down in between them. So that's what the Portland Basin is. It's a rhombochasm. It's a pull-apart basin, and the rivers have come in and filled in with some sediment. But basically, the basin has been there for at least 25 million years. It's part of an extensional topography, which means it being pulled apart. And you might know these terminology of the Horst and Graben, where I guess Graben is German for grave, and Horst, I don't know, maybe that's somebody's name. But in any event, you get this pull apart topography. Someone was mentioning basin and range topography earlier, coming up through southeast Oregon and northwest Nevada. You see the basin and range on a much larger scale. These are mountain ranges and valleys. But here in the Portland Basin, if we look into the east side, now we're looking toward Mount Hood. You can see it's Mount Hood in the distance, but in the foreground, there are all these lumps. And these are fascinating because in the first instance, they are horsts. They're all surrounded by normal faults, so they've all popped up because of that extensional topography. But in the second instance, they are also volcanics. And named after the town of Boring, they're called the Boring Volcanics. They're about 2.6, oh, and there's my house. They're about 2.6 million years old. And a lot of them have river rock on the top because they're horst, they've been lifted up, but they have volcanics around them, either cinder cones or even shield volcanoes that are these mafic, runny, basaltic volcanoes. And they are, as old as 2 million years old. The mountain in the background there, Mount Hood, is also about 2 million years old. But you can see something is very different going on, that the mountain in the background is sharp and pointy. It's a stratovolcano, and the mountains in the foreground, or those hills, we call them buttes, are low and sloping. Typical of the basaltic shield volcanoes that you might see in Hawaii, because it's runny basalt, and so it creates either shield volcanoes or cinder cones. So we've had about 60 or 70 of these little cinder cones and volcanoes, the Boring Volcanics, in the past 2 million years. And we're really one of the only cities in the country that has a volcano in our city boundaries. This is Mount Tabor, and you can see, this is one of our field trips, pointing out there the strata and the cinder cones is it's coming at a diagonal because it's draping over the sides of the cinder cone as it's built. This is what it might look like if it were to erupt in the middle of Southeast Portland. But actually, Mount Tabor itself is dormant, so that won't happen. But we are still in this period of volcanism. So we can expect in the Portland metro area another one of these little shield volcanoes or cinder cones popping up in the next maybe 15,000 or 30,000 years. So that's not something we worry about, or we try not to anyway. We have other things to worry about that I'll tell you about a little later. The big story with subduction, of course, is that as that oceanic plate descends, at about 60 miles down, it starts to release the water that's in it, and the water rises as heat rises. And as it does so, it goes up into the continental rock, causes that rock to melt, which in turn rises as magma as heat rises and eventually erupts into stratovolcanoes. So that's the difference between the low-lying basaltic, mafic shield volcanoes and the stratovolcanoes, is that the magma has had this chance to move through the continent and pick up all the silicate minerals and erupt as andesitic or rhyolitic stratovolcanoes. So the entire Cascade Range, all the way from Canada, Mount Baker, Mount Rainier, of course, Mount St. Helens to our Mount Hood, down through Three Sisters and Crater Lake, which is former Mount Mazama, into California, Mount Shasta and Lassen. All of that is basically the surface expression of where that subduction zone reaches about that 60-mile limit. So what you're seeing is the trace of where the subduction zone is sort of bleeding its water up and causing the melting and causing the volcanism. One river crosses, and that's the Columbia. Now, cool geologic fact, some of you may know, which is that when you have a river that in its entirety crosses a mountain range, it means the river was there first and the mountain range came up after. So the Cascades in their current position have been there for 5 or 10 million years. Before that, they were in another position more inland. But the Columbia, or some river like it, has been draining the Pacific Northwest for 40, 50 million years. That is critical to the Portland Basin story. This is our beautiful scenic Columbia River Gorge, and it has been the source of 3 catastrophic floods over geologic time. First, the flood of basalt, the Columbia River basalt, 16 million years ago, a river of lava which flowed from eastern Oregon and Washington through the Cascades all the way to the ocean. And the Missoula Floods, 18,000 years ago, a river of rock and ice, which again flowed from eastern Oregon and Washington through the Cascades, through the Columbia Gorge, filling up the entire Willamette Valley, and then out to the ocean, and then finally a flood of European settlers in the 1840s, 50s, and 60s. Now, I'm one of those European settlers, although I didn't come until 1979 out of Burbank Airport there. And I found this photo. It's actually from 1979, and it reminded me of, maybe some of you remember, of the time when jet airplanes had smiley faces on them. So let's start with the Columbia River basalts. This is an incredible story. 17 million years ago or so, these giant fissures opened up in eastern Oregon and Washington, and lava flowed out. Again, this very runny, mafic, basaltic lava, and it filled the entire river basin. And as the lava moved west, the only place it could pass in the Cascades was where the Columbia River, the Columbia lowland, where the Columbia had gone through the Cascades. So that lava flowed all the way out to the ocean. And in fact, it invaded the subterranean sediments there into the ocean and reemerged as subterranean, as undersea volcanoes. So if you go out to Haystack Rock, if anyone has seen that, that's one of the iconic photos of Oregon. I didn't put it up here, but that is an undersea volcano of these Columbia River basalts from 400 miles away that may have taken months or maybe just weeks to reach the ocean and then re-erupt. Now, as you see, it's flowing over the Siletzia and Waverly block that we already talked about. So now we've got 2 land building events. We've got the original accretion of that basaltic block, and then now we've got the Columbia River basalts on top of it. Those flows were tens of feet,
Wow.
hundreds of feet. This is from the Columbia Gorge. So that one particular flow that you can see there was 100 and something feet high. And of course, the cool thing about basalt when it cools, the cool thing is that it cracks, and it cracks perpendicular to the cooling surface. So here the cooling surface is the flat, the top, and so you get these vertical columns, these nice hexagonal columnar basalts. This is a video that we took on a field trip a couple years ago. One of our board members, Dennis Chamberlain's drone, flew over one of those fissures, one of those dikes of basalt, and the country rock is eroded away from it. So what you're seeing there is the remnant of that dike, and it's probably about, I mean, my estimate from the drone footage here is it's probably about 50 feet high, about 15 to 30 feet across. I could be off by a factor of 2 or so, but anyway, it's quite striking as you're driving along the road. And if you can see behind those layers there are behind it, maybe I can stop it. I don't know if I can I? Yeah, I think I can. Can you see my mouse? This is,
yes.
Okay, so these layers are the picture gorge basalts, which are some of the Columbia River basalts. So this gives you an idea of the layering of these basalts. And then this was one of the feeder dikes that erupted in over several 100,000 years, probably in that 17 to 16 million year period. So going back to the Portland Basin, our basement rock is that Siletzia basalt. Then on top of that, we've got the Columbia River basalts. And then on top of that, the river sediments that have been brought in through the Columbia and Willamette. And that takes us to our next dramatic story, which is the Missoula flood story, or the Brett's flood story. Now, as we know, during the last 2 million years of ice ages, and particularly in the last ice age, giant continental glaciers invaded the United States from Canada. And in doing so, they blocked many of the river drainages, including the Clark Fork over there by Flathead Lake near the Salish and Kootenai Reservation. And it turned Flathead Lake into a much larger lake that you see over here, Glacial Lake Missoula. And that was dammed by this lobe of ice that covered the Clark Fork. Well, that dam broke multiple times, we understand. And as a result, all of the water, all of the rock and the icebergs and everything that was in Glacial Lake Missoula flooded out into the channel scablands, or created the channel scablands, carved out dry falls, went through the Wallula Gap. And once again, where does it get through the Cascades? Well, it follows the path of the Columbia River. And by this time, there's a Columbia Gorge. It comes roaring through the Columbia Gorge into the Portland Basin, down into the Willamette Valley, and it kind of sloshes around in what we call temporary Lake Allison. And then eventually it drained out to the ocean. So looking at an inundation map, this is the Portland again with the Columbia and the Willamette rivers, and you can see that it inundated to a height of 400 feet. So it was quite a dramatic event if you happen to be there. And there are Calapooia accounts of a giant inner valley flood. So it's possible that there were people at the top of that. This is one of these volcanic buttes, one of these forests, and it's just high. It's just above 400 feet. So it's quite possible that there were people who survived it. But all evidence of their existence would have been eradicated by the tremendous floods. There's I think she's ABD, but she's about to be a Dr. Gail Woodside at OSU, sorry, who's done some work to show that the tensile fibers of the ropes that they were using at that time could have been enough to hold canoes in place for people to be able to escape these terrible floods. So that is a tremendous thing to imagine. If you were in the valley, and now I'm showing again the geologic map with the Columbia at the top there and the Willamette coming in from the south. This geologic map shows that as the waters poured in at about 60 miles an hour into the basin, as they can spread out, they slowed. And as they slowed, they dropped their heavier loads of boulders and gravels. And what that leaves behind are these cross-bedded gravels that you're seeing here. This is a quarry cut from actually on the Vancouver side of the Columbia. And that quarry cut is about 10 years old. And you can see it's pretty enduring. It's pretty hard. There's been a little erosion, but it's pretty tough stuff. It creates these cross beddings that as the water pushes, it creates successive layers of sort of in diagonal beddings, which is something you see in rivers. But here it's on a much larger scale. As the water slowed, they had a chance to drain out slowly through following the Columbia out to the ocean. And here they leave a different kind of record. The first thing that happens when the water's still is you get your gravels, lighter gravels drop out. And then slowly you get your sands and silts. So that's one flood right there. Then maybe there's another 50 years, you get another flood, maybe a smaller flood. So there's a layer of gravel, and then there's a layer of sand and silt. And then beyond that, another and another. And this is how we know that in the Portland Basin and Willamette Valley alone, there were 40 of these catastrophic Missoula floods that came in. Now I'm going to show a video. It's a little choppy, but it'll give you an idea of some of the complexity of how these things overlay.
Hmm, 40 times, wow.
So what you've got there is 40 floods, and then an interval between each flood, some erosion, and then another 15,000 years of erosion and reworking of those sediments. That's particularly interesting to me. I live, right, as I said, right next to Reed College there. I'm in between, right on the border of two units. So to the west of me, to the east of me are these coarse grain deposits, those gravels, and to the west of me are the fine grain deposits. Reed has a nice little pond in the middle, so you can get down there and you could see some of the sand, some of the gray basalts there. But they're really just diagnostic rock for this are these little orange rocks that some of you will recognize pretty quickly as from their sugary quality as quartzites. And so for there to be a quartzite here, that's a metamorphic rock. We just don't have metamorphic rocks native to Western Oregon. We're too geologically young. This rock had to be, well, it might have been a granite at one time that was uplifted in the mountain and then eroded into a boulder and a cobble and sand and then covered up in the sea and lithified and then under a continent, under a mountain range, metamorphosed into a quartzite, then uplifted again, then eroded into a cobble and so forth. In any event, it's very old, probably in this case, 1 billion years old. And we suspect that it's from the Montana fold belt. So it would have come through again, the drainages of the Snake or Columbia River. And you often find these actually in Columbia River sediments that are older, but in this case, it's diagnostic for showing us that this came catastrophically all the way from Flathead Lake into the Portland Basin. Finally, another feature, dramatic feature of subduction zones is they get stuck, this conveyor belt, and then they get unstuck and release catastrophic earthquakes, such as the Tohoku earthquake in Japan in 2011. So you in California have known about earthquakes since the 1906 earthquake, and you're pretty well prepared. For a long time, it was thought there weren't any earthquakes in Oregon and Washington. And well, it was thought by science. There are stories of Native American stories of Thunderbird and Whale that go back to time immemorial. And there were other clues. There are, for example, these tree stumps that show up at low tide at some places on the Oregon and Washington coast. The tree stumps, if you look at them, if you do the dendrochronology, looking at the tree rings, they all died in the same year. And the thinking is that when the tsunami came in, and because the land drops after one of these earthquakes, that the trees get inundated by sand and they die. And so they all died in the next season. So that was a clue. But the smoking gun was what's called the orphan tsunami. And Japanese keep very close records of tsunamis and earthquakes. And tsunamis typically, because of the wavelength They follow about 15 minutes after an earthquake. So there's usually a pretty tight connection. But there was one earthquake in 1700 that had, or one tsunami that had no earthquake attached to it. And so the scientists have figured that, assuming that tsunami waves travel about the speed of a jet aircraft, about 500 miles an hour, that you can back up the timeline and figure that the last earthquake in the Pacific Northwest was January 26th, 1700 at 9 p.m. You know, personally, I think the 9 p.m. is just scientists showing off. But in any event, looking at the record, it seems that there's been one of these catastrophic 8 to 9 magnitude earthquakes, looking over the past 10,000 years, on average about every 300 years. So if the last one was 1700 and it's 2021, that's 321 years. So some way scientists express this as being 9.5 months pregnant for an earthquake. Or another way to look at it is statistically, we've got about a 30% chance in the next 50 years. So going back to the geological story here, I'm going to overlay on the geological map a earthquake hazard map, a liquefaction map, in fact. And it means pretty much what you'd think it means. The red is bad and the lighter colors are better. And the worst place, as you can see, is kind of down by the river, because what they did in the late 19th century and early 20th century is they dredged, they vacuumed up the bottom of the river, and they built up the floodplains and the marshes around it. They filled them in so that they could have more ports and more industrial space. And unfortunately, that's where they put 95% of Portland's energy infrastructure, what's called the critical energy infrastructure. Fossil fuels there in tanks, some of them 100 years old, many newer. In any event, they're all on this fill. And you're in California, you probably know about liquefaction. If you've got sand or soil and it's moist, get an earthquake, it basically turns into a liquid. So the tanks will fail and they'll catch fire and they'll release ammonia and chlorine and other burning petroleum fuel pollutants. And then they'll float downriver and cause environmental catastrophe. So this is what we worry about. And some of us are involved in efforts to regulate, at least, and make the critical energy infrastructure somewhat safer. The next worst place to be, or the next least worst place to be, is in those Missoula fine sediments, which are probably okay if they're dry. But where they're wet, there might be more chances of liquefaction. We do get a bit of rain up in Portland, so there's some risk there, but the best place to be, of course, is on those Missoula gravels. Those cross-bedded gravels are, great to have your house on. Hard, a little bit hard when you're gardening, but my house is right there, right on the border, right in the realm of uncertainty, where I'm not quite sure if, I think my hill, because I garden, and a few years ago, my wife wanted to strip off the ivy, and I was like, I don't want to do that, because I didn't want to do the work, but I was worried that the hill was going to come down. We took the ivy down, and we've been trying to plant other things, but the hills remained rather stable. And part of that is, my hope is, it's because of these gravels. They're just really tough. So, well, this is not an ad for Simpson Strong Tide, but we're trying to catch up with you in Oregon. We're trying to catch up with California in terms of, in this case, bolting my house down to the foundation so that at least I'll be able to shelter in place after an earthquake. So that's the end. But wait, you say, there was one character you mentioned earlier in the story that you haven't gone back to, and that is the hotspot. What happened to the hotspot? The story of hotspots is, we think they stay put. They stay in one place. So looking at the Hawaiian hotspot, for example, the youngest volcano is Loihi, which is undersea at this point, and it's to what would be the southeast of the big island of Hawaii. Then we have Kilauea, which has been very active in 2018, for example. And then they just get progressively older as you go to the west. So you get Maui is 1.3 million years old, and Molokai, and then Oahu is 3 million years old, and on and on and on and on, going to the west, all the way into the Emperor Seamount, which are seamounts where the above sea level part has already eroded away, and you've got these seamounts underwater, going back 50 million years or more. So this is a classic example of mantle plume staying in place, plate moving over the top. We know that Siletzia erupted, those volcanics erupted 56 million years ago, and then we believe they accreted 50 million years ago. So this again is that map showing the accreted Siletzia block. And then there were some more volcanics that occurred in the Eocene that I'm kind of skipping over, although those are tremendous stories in themselves. And that's a whole nother lecture. But there was a quiescent period of 10 million years or so. And then there's this tremendous outburst, the Columbia River basalts 17 million years ago. These tremendous flood basalts that mainly for a period of 2 million years, but then going to about 8 million years ago, there were still these basalts were coming out, and also the Steens basalts in Southern Oregon. Then we've got calderas forming. And you can see the progression here, the pink circles, that's 16 million years ago, 13 million years ago, 12 million years ago. You see what's happening here, or how we explain it is the mantle plume is staying in place and the North American continent is moving over the top. 10 million years, 10 million years, 6 million years, 2 million years, and then 600,000 years ago, yes, the Yellowstone caldera. So this brings the whole story together. And my wife and I were at a banquet a few years ago. Nick Zentner, who's a great educator, and I really recommend his stuff on YouTube, was the first one to tell us about the hair on the back of our necks went up, because this brings the whole story together. What's unique about the Pacific Northwest is you've got both that subduction story with subduction volcanism and the Cascades, but you've also got the intersection of this hotspot story, which ties in Siletzia, the Columbia River basalts, and the Yellowstone caldera. So it's fascinatingly complex, and this is a seismic tomogram, which is basically like a big Earth-sized MRI using earthquake waves to get a three-dimensional image. And this is the work of Karen Sigloch and her collaborators. It gives you a glimpse of an idea of how, when instrumentation improves, you get a sense of a much more complexity. And so that simplified picture I've been showing you of the conveyor belt with the subduction zone, that's still true, but there's something much more complex going underneath that involves the intersection of these really two different kinds of phenomena, the hotspot volcanism and the subduction volcanism. So one of the great things about geology as a science, and those of us who are in amateur clubs, is you get to rub shoulders with the scientists who are doing this work, and go out on field trips and listen to them talk about places where they've actually done research, and listen to them stand in front of outcrops and say, I don't know. What do you think? So that's one of the great delights for me, of being part of the Geological Society. It's available now, as you've shown here. The unfortunate pandemic and the growth of Zoom has opened up so many doors in terms of having connections with other clubs. And we've really appreciated our connection in recent years to the gem and mineral folks, because you guys have a much better sense, first, of mineralogy, I have to say. Most of us are interested in sort of the overall plate tectonic narrative, although we have some petroleum geologists and other working geoengineers and so forth too. But you folks have a much better sense of mineralogy and the aesthetics, which is an important piece. So I've appreciated my connections with the gem and mineral societies and our local ones, but also remotely. You can attend our meetings, and the next one coming up is by the guy who wrote the book on Oregon geology. Dr. Bill Orr is a friend and member of the club. He's going to be talking about 20 scientists he's known and admired. You can register at our website, gsoc.org, for our Zoom meetings, and the next one comes up Friday, September 10th at 7:30. We had a meetup that we were doing at a deli. COVID put an end to that, but now we have, oh dear. Now we have our monthly geology talk, which is a Zoom meetup, noon on the fourth Saturday of the month. We have a graduate student from Portland State University, Andrew Dunning, who gives us the geology news, and then people share pictures of rocks and talk about geology and just generally socialize. So that, again, is fourth Saturday of the month, and I guess, well, we're in September, so that's coming up. So that's where I'll stop. I'll take questions or answers, and one of the things I'm particularly interested in is, I didn't mention this to you, but I'm actually in my parents' home here in Northridge. So I'm actually closer to you than I was when we first set up this date. And so I've become very interested now that I'm looking at I'm looking at the hills over in Chatsworth. I've become very interested again in the geology of Southern California.
Well, thank you, Paul. Does anyone have any questions? You could unmute for your questions.
That was fascinating. Thank you.
Thanks. It's good to hear.
Paul, do you know much about Spokane area?
No,
Okay.
but I can take a crack at it. But what are you thinking about?
Oh, I'm moving out of crappy California and moving to Spokane.
All right.
And I was curious because I know there's a lot of basalt along the Spokane River. The waterfall over in town from the water and power company is all in basalt. And I was just curious if you knew any of minerals that are up there or anything like that.
I don't. I mean, what's interesting about that part of Washington and Oregon too is you got the older continental crust, and then you've got accreted terrains, and so you do get some pretty interesting mineralogy. The mineralogy is out there is much more interesting than Western Oregon, which is mostly just basalt. So I would really recommend listening to Professor Zentner's lectures on because he's done a lot of work on those terrains out there in Eastern Oregon. And it's fascinating. It's complex. I've kind of mastered to a limited extent the Portland Basin story, but man, you get up there in Washington and there's a lot more. California is the same way. It's not that Oregon is simple, but when you get these older terrains, like I'm here in Southern California, and you've got the San Gabriels and you've got, billion-year-old stuff just a few miles from here. It's a much more complex story. So I think in the Spokane area, it's gonna be pretty fascinating. I would also recommend Dr. Marley Miller's book. It's one of these roadside geology books, and they just came out with a new edition of the Roadside Geology of Washington. And I find her books that whole series is a great way to kind of, learn along the highway that you're traveling, kind of what the outcrops are.
Oh, okay, great. Thank you very
Good
much.
luck on your move. Yeah,
Thanks.
sure.
So I have a question. I'm actually in Portland. I'm in St. John's. So, but I grew up in Southern California with Nancy and Gail, my sister.
Okay.
Can you are you able to talk a little bit about like the dinosaur beds that are out in John Day and also Prouty Ranch? Like, how did that part of Oregon come to be so different than the western part of Oregon?
Yeah. Hey, that's a great question because you set up something that I wasn't able to talk about when I was going quickly from Siletzia 50 million years ago to the Columbia River basalt 17 million years ago. Back in the Eocene, very warm period when there were lots of very strange looking mammals running around, everything had big horns, even the gophers. And if I grew up on these Time Life books, and there were these fantastic pictures of the mammals of the Cenozoic. And so it turns out that's
we did too. Dad had all those for us. Yeah.
Good. Well, and the whole story of the evolution of the horse and the simplification of the horse hoof from 4 to 3 and 2 and so forth, that gained much of the evidence for that came from Oregon's first geologist, Reverend Thomas Condon, working in the 19th century in that John Day area. Because what happened in the Eocene is that hotspot, this is our understanding now, that hotspot moved under the middle of Oregon and erupted these tremendous, what are they called? Well, stratovolcanoes, not the pointy stratovolcanoes, more like the Yellowstone calderas, with tremendous ashfall, covering up marvelously all of these fantastic mammals. So it's not dinosaurs because it's Eocene age. It's all these Cenozoic mammals. We don't call it the Cenozoic anymore. What do we call it now? Neogene, Paleogene. I think it's Neogene anyway. So when you go out there, you see in part, go out to Blue Basin or something, and you see these tremendous ash tufts. And they just blanketed it. It was a terrible, catastrophic event if you happen to be.
It's like feet deep. Yeah.
And then it erodes into it's beautiful colors because of the minerals in the beautiful green, for example, and then it erodes into these spectacular formations and so forth. So that's part of it. And then you've also got the painted hills out there, which shows the sort of climatic variation. So that's a wonderful, wonderful part. That was when I was president of the Geological Society, that was our our field trip out there, because that is magnificent, bizarre terrain and really a great
Yeah.
part of both paleontological and geological history.
And so like at Pridey Ranch, so Pridey Ranch is a place we went a lot as kids with our folks. The thunder eggs that are there, are those coming because of the volcanic explosions from the Cascades, or what's driving those?
Yeah, that's another great question, and we don't completely know with the thunder eggs, but
Really?
yeah,
Okay.
there's, I mean, I think because no one has ever seen one hatch in real life or something.
Right,
But
right,
the thinking is that it is those rhyolitic tufts. But you know, once you have one of these catastrophic volcanoes that throws all this ash, and then it's hot, and it actually, even though it's landed, there's still sedimentary processes going on. It's still sort of semi-liquid in a sense. So you'll get flame structures coming up, and I think the thinking is that you get some of this reworking you know, I'm talking out of my, I don't know exactly what I'm talking about, but
Okay.
this is what I've heard, is that the thinking is that it's those rhyolitic layers,
right.
and then magic happens or something.
Okay.
So
Sure, that's what we also call science.
Yeah, science, right.
Thank you very much.
Sure, fascinating stuff. And I think that's our Oregon State Rock, or
Vale. I can tell you all about thunder eggs and how they happen.
Okay.
I can share that now, or we can share that later. The crowd's choice.
Oh, maybe you could do a program for us.
Tell me, because yeah.
Go for it.
Okay, so you're right about the rhyolitic flows
Okay.
and the pyroclastic flows, and they are tremendously hot. They lay down the material, and it creates voids of gases. As the material begins to settle, it hardens, and that's what the brown crust is on the Pleiadae formation of the rhyolites, of the thunder eggs. So then as fluids that are silica rich, because the rhyolitic flows are silica rich as to opposed to andesitic flows, when the water comes in, it's still hot, it's under pressure, it dissolves the silica, and then the silica gets into these voids, it loses pressure, and then it allows the silica or the quartz to begin to develop and create fill in the voids, which are the thunder eggs.
Okay, so it's actually somewhat similar to the process of zeolites forming in the vugs of the basalt, except that's a cold phenomenon. What you're describing sounds like it's still pretty active. That's fascinating. Okay,
it's very similar, and Dick Wegerberg can back me up on this. It's very similar to how subterranean nodules form, where the minerals begin to concrete out of the surrounding material because of pressure and temperature changes as it hits voids.
and so in those thunder eggs, I mean, basically, it's agates and jaspers?
Yes, the rind, the brown rind that you would find around a typical thunder egg is going to be your rhyolites. That is the material that the silicas came from. The inside that ends up being the either the moss or the dendritic or just the plain blue and white banded scenery that you would typically find in an Oregon thunder egg is your silicas and any impure minerals that were trapped inside like your chrysobalites and your zeolites. There are known incidences of zeolites. And as these begin to settle out because of pressure differentials, temperature differentials, they precipitate out at different rates, and that's why you end up getting the layering and the pictures that you see when you slice up a Pleiadae thunder egg.
Yeah, the thunder eggs coming out of Pleiadae are gorgeous.
I think I've got one sitting right over here.
Do you have one, Gail? Can you show it?
Oh, I'm sure there's one around here somewhere.
Yeah.
The opalization.
Because I think Gail and Nancy and I for sure were there at least 2 or 3 times pulling out thunder eggs as kids, and it was such an exciting thing. to pull out an
that was
egg or a triple egg and then watch my dad cut it, and it was really fun, and I didn't know very much about it. So thank you for that. That's great. Thank
you're
you.
welcome.
And we do have some agates that erode a similar process with the basalts that erode out of the Columbia River basalts. So it sounds like it's a similar process, but again, it's colder and longer, probably taking longer.
Fascinating.
All
Thanks,
very
Brett.
interesting program. We definitely enjoyed it this evening. Since you're in the San Fernando Valley, Dick and I would like to invite you, if you are interested, to an in-person meeting of the Del Air Club tomorrow evening, if you're going to be around.
Oh,
Dick
well, I would love to. My daughter's coming in tomorrow. We're moving house. This is my parents' house. I've been here for 55 years, so I'm in Northridge. But I would love to meet you at some point in the future when I'm back down here in Los Angeles. Tell me again what the club is or what the group is.
It's Del Air. They meet over by Cal State Northridge.
Oh, really?
Yes, and this will be their first
So-
in-person meeting.
What time?
7:30.
7:30.
So, well, maybe I'll get my brother to drop me. Can you give me the address? Because we're right. My dad taught at Cal State, and so we're just right next
You're
door.
probably
so-
2 miles away.
Yeah.
Why don't you get the contact info from either Stephanie or Gail, whoever has
Yeah,
it.
send it to me. I'd like to drop in.
Anyway, if that doesn't work out for you, and we certainly understand, next month the Oxnard Club will be having the same presentation, and Dick is giving it on the national parks in California.
Okay.
Oh, great.
Yeah, for those of you who read the newsletter, it said California's state parks. That is not correct. It's the national parks in California. So anyway, Paul, if you
sorry.
missed the meeting tomorrow night,
Okay,
and I
thanks.
certainly understand that, you can tune into the Zoom meeting here next month and see it.
A bunch
All
of
right.
it's actually on Lassen, so you'd be interested in that.
Oh yeah, Lassen is great.
Yeah. Well, I'm going to thank you all, and I'm going to sign off and get back to packing. But it's delightful to meet you, and thanks for the invitation. And I do hope. Will some of you?
Thank you.
Will some of you be
much.
there tomorrow?
Yeah, it's a great
All right.
program. Thank you so much.
Okay.
Yes, thank
Thank
you.
Thank you,
As
and
your
go to
as your
gsoc.org and
Portlander,
come to
I
our meetups.
appreciate it.
One
Okay.
thing is
Right
that
on.
we think you're very, very funny,
Thank
and
you.
your terrain wreck was as hilarious. Right? Was
They're
right
kind
up
of
there
dad
in
jokes,
your
but they
world.
work. Thank you. That's very kind.
your
That's
humor.
very generous. I appreciate that.
I wrote it
All right.
down.
Good night to you
Terrain
all.
wreck.
Thank you.
Paul,
Thank you. Thank
Paul,
you.
Thank
So
you.
someone is calling out.
Paul,
Yes.
go down Reseda to Van Owen, make a left about 50 yards. One of the best Mexican restaurants you'll have. It's called Las Fuentes.
Las
Ah.
Fuentes.
Yes.
I'll do it. Okay. Thank you. Thank you. All right.
Nancy
Good
knows
night.
Las Fuentes. Yeah.
It's good to
Thank
know.
you.
Bye.
Thank you,
That's
Thank
where
you.
I'll be tomorrow.
Thank you.
Bye-bye.
Bye.
Thank you, Adrian.
Awesome.
This was
Yay.
really interesting. Thank you so much for inviting me.
We're always welcome.
Thank you. I'm
Definitely.
gonna try to be with the national parks. Well,
Cool.
Gail and Nancy know I'm doing a master's in public history, and one of my courses is on the history of national parks. So I'm definitely gonna do my best to be there next session and listen to national parks. That sounds awesome.
Very cool. Love it.
Right on.
Well, you're welcome, especially if you
Thank
tell
you.
stories about Gail.
Oh, I have so many
Wait a
stories to
minute.
tell about Gail and Nancy. But
No,
mostly, I will tell
no,
you that she's one of the best sisters anyone could ever have.
I
Wait.
believe that. I totally
Wait,
believe
how
that.
is that possible? She said that
Likewise.
about you two.
Oh,
Yes.
that's very sweet. No,
Yes,
I
yes.
feel like, so Gail and Nancy and
one
I
of the
grew
best
up
cousins in the world.
not as
Yes.
not so I don't feel like we're as cousins as much as we're all sisters. And it's such a gift to me to have Gail and Nancy in my life. So
That's awesome. What a blessing.
And Gail
Thank you.
is a taskmaster and I need it. So it's all works out the way it's supposed to.
Well, she does a wonderful job at the programs.
Oh
Clearly.
my gosh, I
As you
know.
have
It's been
seen.
so exciting to watch the program. So thank you for having me.
Thank you.
Thank you
Thank
for
you.
joining us anytime.